Welcome back, students. Let's go to another exercise problems on power series method around an ordinary point. We're talking about this problem now, and this time the power series method will make more sense because we have variable coefficients. Please note that both of these functions are differentiable arbitrarily many times around t equals to 0, or as a matter of fact for arbitrary t in this case, because denominator never becomes 0. Please note that denominator stays positive all the time. Let's increase the font a little bit further. 1 plus t squared stays positive all the time. In any case, let's do this around t equal to 0 again. All right, here's the first step, and let us remove the denominator. Okay, and then let us put in the power series expansion back into the original equation. Let's see. I did some color coding here. This is the original power series expansion, Cn t to the nth power, and blue we get by taking the derivative. Red, we get the second derivative. And then if I put everything in, we get this equation, right? This is y double prime, red, or, okay, red, and that's blue. Okay, all right. Red, I didn't mean purple, excuse me. And then speaking of purple, okay, let's put this one into purple. So this one is purple, and rest of the expression is black. Okay, so far so good. Now please note that I didn't do the index shifting yet. It's gonna be counterproductive if I did that, because it's gonna be screwed up anyway, again, by this t squared and t. What am I talking about? Let's go to the next step and it'll become a little bit clearer. Let's see. Okay, let me see. This one and that one both came from the red series. Just distribute 1 plus t squared, and then we get that. And then the next one, just blue series. And then the purple series, let's just keep them as they are. And then let's work out some further computation with this t squared and t. All right, and I'm gonna throw away all the color coding now. We already saw where this and that series is coming from. They both originally came from y double prime through this and that. And then this one came from y prime via this and that, and so on. All right? Okay. This one, no change. This one, now I have to multiply t squared to each of this t n minus second power. And what do you get? T n minus second power, and then times t squared. So that's basically what happened here. N minus 2 plus 2, so you ended up with t to the nth power. about this one? N minus first power, but here's another t. So basically what happened was n minus first power plus 1. So eventually what do we have? We have nth power. All good. All good. All right. Okay. Now please look at the 3 series. These. All these are good. They all have t to the nth power. Not this one. Not this one. So let me apply a color coding now. Green is too bright, so I'd better make it a little bit darker. Okay, let's work something out with this one. And then that's the next portion here. Oh, okay, I didn't have to do this color coding. Let's go back to black. Okay, I just copied all that down here. Okay, all right. And then I just use, let's see, this a little bit brighter purple, plum color, okay, for the first series. And because I want to keep it into nth power, so let's take a look at this colored part a little bit more closely. We want nth power. So what did it do to this n minus 2? We replace this to n plus, no. Okay, all right. Let's bring it down here. Okay, okay. This one. Text color. Is it this color? Okay, all right. All right. And then let's replace n by n plus 2 so that you get nth power in the end. So this should be n plus 2. That 2 should be n plus 2. And this one should be n plus 2 as well. And finally, that 2 is n plus 2. Simplify this. This n plus 2, n plus 2. This n plus 2 minus 1, n plus 1. This n plus 2, yes, we have n plus 2. And t, n plus 2 minus 2 becoming t to the nth power. That was by design. And then index as well, n plus 2 is equal to 2. So beginning from n equals to 0. That's how we got this index shifting done to the colored part. Okay. Let's have a brief recap. This is the original equation. All right. Denominators are harder to deal with, so let's remove those. And yes, we can do that because denominator never becomes 0. So multiplying by absolutely non-zero term to all term, yeah, we get that. And then apply power series and then apply term by term differentiation and plug those in. Color coding would help. Olivier algebra distribution, and then one more computation, t squared applied, t applied, and we get that, and then index shifting. We get final expression up to now. Okay, in a final expression here, we're gonna take t to the nth power out, but you have to be a little bit careful here. N going from 0, this n goes from 2, that n goes from 1. They're all different. So starting from n equals to 2, everything is common. When n equals to 0 and 1, things are a little bit different. Okay, all right. I think this is, I think this part is redundant. Why did I do this? Oh, I see. It's the same thing. I just did a color coding to prepare for the next step. Oh, no, excuse me. Sorry, I'm confusing you yet again. Sorry about that. The difference lies on the indices. Sorry about that. You see, all these indices are different. N equals 2, n equals to 1, but it is possible to get everything starting from n equals to 0. Why is that? Because when n equals to 0, this whole thing is 0, so adding 0 doesn't change anything. When n is equal to 1, then this is 0, so that whole thing is 0. So n equals to 2, n equals to 0 makes no difference because we are just adding 0 twice. Same thing went here. N equals to 1 for that, but n equals to 0, so adding 0. So from here to there. Okay, we are ready. Take t to the nth part out. And then what do we have? Black part, and this is the blue part. That's the red part, but in any case, we get this whole thing. And then each coefficient has to be 0, so we ended up with this recursive relation. We have c of n plus 2 and c of n, so you can solve for c of n plus 2 algebraically, and then you're going to get after some simplification, you're going to get this. C of n plus 2 is negative of c of n. Some brute force algebraic computation. So taking these parts together, factoring, and then eventually we have common parts, so we ended up with this simplification. In general, this becomes rather dirty computation, but for this particular example, it turned out really simple. We're just lucky. Okay, now that we have this recursive relation, we can find out all those coefficients accordingly. So negative of c0, negative of c2, so positive of c0 again, and so on and so forth. We get just alternating sign, and same here, alternating sign. So for the evens, we have this. For odd, we have that. And what do we have? We have two linearly independent solutions. This one and that one. And then we have c0 and c1, which are just arbitrary constants. As for some little sign mistake, you don't have to worry about it because these will be arbitrary, so they're going to be observed anyway. By the way, do you recognize these functions? What is this function and what is that function? They both come from geometric series, as a matter of fact. Geometric series. The detail is left to the student. How do we end up with geometric series like that? It's Calc 2 problem. Oops.